This is the second part of energy in SHM oscillators. If you've not watched the video where it's related to position, I suggest you do that one there. What we're going to do is, rather than think about how the energy is in different points of the cycle in terms of where it is moving backwards and forwards, I want to think about how it is in time. And I'm going to do this again in two different ways. I'm going to first of all start off with potential energy PE. So PE for our mass on a spring is equal to half kx squared. So we need to think about how we can, rather than get rid of the position, bring in time into this, and we can go x equals a cos omega t. So I'm going to substitute that in. First of all, I need to square it. So a half k a squared cos squared omega t. So here we have a function for the potential energy as a function of time. This true only for a mass on a spring, obviously, because I've used half kx squared. Kinetic energy is equal to a half mv squared. Now we need to get rid of the v. M is a constant, half's obviously a constant, so we need to find an equation to bring time into this equation. So we're going to go v equals minus a omega sine omega t. So we need to square this to substitute it in. Maybe I'll just do this under here so it's a bit clearer. Well, the minus is going to go if we square it, so we're going to have a squared omega squared sine omega t. Not sure how much trick you've done in maths, but don't forget that the sine goes after the n, not at the end. There. So I'm going to substitute that in. So half a squared omega squared sine squared omega t. And then the total energy is the same as it was before. So the total energy is, well, this cos squared. So there are moments in time when all of the potential energy is when all of the energy is in the form of potential energy. So total energy equals PE max, which equals KE max. So we've got to think about when this function is at a maximum, and it's a half Ka squared, which is the same equation we had from the previous video, and then the Ke max, well, sine over time, these are all constants, this is the only thing that varies with time, so sine is a maximum of 1, so sine squared is a maximum of 1, and that just drops out, so we have a half a squared omega squared. So there's a few things to note on this one. If Ke is the form of sine squared, even if it's not a mass on a pendulum, not a mass on a spring and it's a pendulum or something else, the potential energy will be proportional to cos squared, whatever type of SHM oscillator it is. The constant at the front will be different, we won't have the K there, and the constant, the total energy is the same throughout. You do need to know these equations. I really urge you not to remember them, but you should be familiar with all of these equations. I've only used a half kx squared, x equals a cos omega t, a half mv squared, and a equals a omega sine omega t. So I would just urge you to sort of remember how you work these things out. So the difficult bit with this, I think, quite often is plotting the graph of this. So we're going to plot a graph here, and I'm going to plot time on this axis. So I'm going to plot two important points. I'm going to plot t, and I'm going to plot not 2 pi, 2t, and then I'm going to put in here, this is energy on this axis, and this is equal to that sort of total energy here. So the total energy is the easy one to plot, because it just goes straight across like that. The total energy is always the same. Now, we've got to plot, let's start off with potential energy. So potential energy is of the form cos squared. So what I'm going to do, what I suggest you do, is you just sketch very basically at the bottom what the cos graph looks like. So the cos graph is like that. Okay, so the cos graph obviously goes from 1 to -1 to 1 and has that time period like that. I'm going to draw the kinetic energy graph, the sine graph, here as well. I'm just drawing these as a way of helping you to sketch the graph. So what I'd like you to do is pause the video and try and sketch what the graph of potential energy and kinetic energy is. Use these sketches here as a rough guide about what they're going to look like. Okay, so off you go, pause the video, try and sketch them, unpause it if you want a hint, and I'll start going through it. Okay, so welcome back. Potential energy. Well, potential energy here, you can see all of the energy is going to be in potential energy there. This is going to be 1 squared. It's at maximum, so it's up there. Here, this cos function is 0. Yeah, cos goes back down to 0, so 0 squared is 0, so the potential energy is 0. Here, cos is going to be -1. -1 squared is +1, and therefore we're going to be back up there. Here, 0, 0 squared. My numbers, my spacing's all got a bit out here. Up there, 0, up there. Okay, so those are the points that we know. So I've drawn that one in the wrong place. There we go. So we need to think about how this looks. So maybe pause the video and think about how you'd sketch this graph, what this graph squared looks like. It looks like this, and the confusion that a lot of students make with this is that these points here are pointy. It's almost like a zigzag. It's not. The gradient does go down to 0 at the top and bottom, so you should have a nice graph like that. We do the same with the kinetic energy. 0 squared is 0, 1 squared is 1, so that's going to be a maximum. This function is going to be a maximum, and that's 1. And then we've got 0 here, and you can see that when one's maximum, the other one's a minimum, which is what we'd kind of expect. There are moments in time when all the energy is potential energy. The other one's kinetic energy is 0, and there are times when the kinetic energy is at maximum, the potential energy is 0. Hope I got that the right way around. So we should have a nice graph like this. Okay, so you do need to be able to sketch this graph in the exam, and I've done the different colours like that. An important point to note here is that this is one time period here. So in this one time period, from here to here, there are 2 peaks of KE, the red peaks, and there are 2 peaks of potential energy. And this is, if we go right back to our mass on a spring, that's what we'd expect. So if we start it, we've started at a potential energy peak, so we've started here, and in one time period it goes from here back to here and back here again. So we've got to think about the potential energy peaks. There is a potential energy peak here when the spring is at its most stretched. There is another, and then goes down to 0, and then goes back to another peak when it's at this point here, moves back to the origin, and then back here. So there's 2 peaks of potential energy in every cycle. Here, here, and then that's part of the following cycle. Kinetic energy is a little bit easier, I think. It's got a peak when it goes past the middle that way, to the left, and then there is a peak when it goes that way through the middle as well. So we've got the 2 peaks of kinetic energy there and there when it's travelling both ways through the origin. We get that because sine only has 1 peak and 1 minimum, but when we square them, they both end up as peaks. Square a negative number ends up a peak there. So we have a graph that looks like that.